Hi folks, Chris McClure here. Last time we talked about computing probability of the union of two events. In other words, the probability that one event happens or some other event happens, or possibly both, using the OR rule. Now, today we'll talk about the multiplication rule, which applies when we're trying to calculate the probability that one event happens and some other event happens. Now we're going to talk about the basic ideas here in section 4.4, and then next time we'll bring in these other pieces involving complements and conditional probability. So today we're talking about calculating the probability of event A and event B happening. And of course we're going to be using the multiplication of those individual probabilities, but exactly how we do that, we have to be a little bit careful, as we shall see. Now, we have to determine whether the outcome of one event happens to affect the other event's outcome. Okay? And if it does, then we have to adjust how we bring in the factor for that second probability. So let's take a look here. The probability of A and B, what does that really mean? That means the probability that event A happens. Now, what is event A? Could be a coin flip or toss of a die or something, and looking at the outcome, whether it's a 1 or tails or an odd number or whatever. So the probability of event A happens in the first trial, so maybe a flip of a coin, and event B happens, occurs in the second trial. Maybe the roll of a die occurs with the 6 showing up, whatever. Now when you see this notation here, this means probability of B given A. This vertical line segment here means given, as in the probability that event B happens given the fact that event A happens. Now, we call this conditional probability, and we'll talk more about it tomorrow. We're assuming that we know something about what has happened with event A when this experiment has happened, and then knowing what this outcome A is, maybe it affects event B, or maybe it doesn't. Depends on if those two events are independent or not independent. Regardless, the probability that event A and B happens is going to be the product of those individual probabilities A and B. We're assuming that event A happens first. So we'll have the probability of event A happening times the probability of event B, conditioned on knowing what event A is, provided though that A and B are somehow connected with each other, and knowing that the outcome of this first experiment somehow determines the outcome of the second experiment, then this will really be a conditional probability. Now, if it turns out that those two events are independent of each other, then the second probability would be the probability for B, and that's it. Because the probability for B given A, again, if A and B are independent, will just be the probability of B. So all we're doing here is we're just multiplying the individual probabilities together. So if we want to calculate the probability of flipping a coin that shows up a head, and you roll a die and it shows up a 6, turns up a 6, there's going to be a 1/2 times 1/6 probability for a 1/12. But if the one event depends on knowing what the other event is, then you'll have to adjust somehow. So, for example, if you want to calculate the probability of, when you draw 2 cards from a 52 card playing deck of cards, you want to calculate the probability of getting 2 spades in a row. Well, there's going to be a 13 over 52 chance that the first card is a spade. But that leaves us with 12 spades out of 49 cards, which is not the same probability as for the first card. So knowing the fact that the first card was a spade will affect the probability for the second card being a spade. So you'll have 13 divided by 52 for the first card times 12 over 49. Excuse me, 12 over 51. So 13 over 52 times 12 over 51 will be the probability of getting 2 spades in a row, because you have to adjust according to the fact that those two events were not independent of each other. But if you want to calculate the probability of getting a heads with a coin flip followed by rolling a 6 with a coin or with a die toss, it's just going to be 1/2 times 1/6, because those two events are not dependent on each other. So again, we've said it many times, verify that the events are independent or not independent and adjust accordingly. And if you are having more than just 2 events happening, then just multiply their individual events. Make sure that you are adjusting accordingly as to whether the events are independent or not independent. So just to reiterate what it means for 2 events to be independent or not. The coin toss and the die toss are independent of each other, because knowing that you got a coin toss resulting in the heads does in no way affect the probability of rolling a 6. But knowing that your first card drawn from the deck was a spade will determine the probability for the second card. So if you want to calculate the probability that the second card was a spade, though, that's going to depend on knowing what the first card was. So those two events would be dependent. Okay? But just because the two events are dependent on each other, or in other words, not independent, does not mean that the one causes the other. Just to let you know. Now, using that adjustment for dependence is appropriate when we're sampling from small populations, but when we are sampling from large populations, it doesn't really matter too much unless you are in requirement of very precise and accurate calculations. There's the 5% guideline that says that if the sample size is no more than 5% of the population, then it's okay to treat the selections as being independent. So, for example, suppose that there are, 5,000 marbles in a bag, 2,500 white and 2,500 black marbles. Well, I want to calculate the probability of randomly selecting 2 marbles. Well, even if you select 1 marble and it's a white, that it's still roughly 50-50 white and black in that bag. So there's going to be approximately a 1/2 chance that the second marble is a white or a black one. Okay? Now, to be sure, if you want the very exact probability, it's going to be 1/2 times 24.99 over 25, or out of 49.99. That is 1/2 times 24.99 over 49.99, which is practically 1/2. So, but it's going to be okay for you to simply write 1/2 times 1/2, because the difference is very small. Here's another example in calculating conditional probability using the multiplication rule. Now, suppose that we have a total of 50 results from doing a urinalysis. drug test. And of the 50 tests, 44 came back positive, 6 came back negative. So if you were to randomly sample 50 individuals, 2 of the 50 individuals, now sample size is 2. All right, that's 4% of the sample. So if you want to calculate the probability that you randomly sample the first individual who tests positive and the second person tests negative, well, the probability that the first person is positive is 44 out of 50. And the word "and" means multiply, and you want to calculate the probability that the second person is negative, so you could take 6 over 50. So you'll have 44 over 50 times 6 over 50. And that is sampling without replacement. Actually, what I just did was sampling with replacement. But as we'll see here, sampling without replacement, there was a 44 out of 50 chance of the first person being positive, and then we have 49 individuals left. There are 6 of them who tested negative, so there's a 6/49th chance that the second individual tested negative. So you multiply their individual probabilities. 44/50 is times 6 over 49. But again, because of the fact that our sample size is small compared to the population size, if you were to do 44/50 times 6/50, your answer would be very close to this 0.108. So don't sweat it too much when your sample size is small compared to the population size. Here's another example. When 2 different people are randomly selected from those in your class, provided that we actually had a class of individuals. Imagine a room full of people. Find the indicated probability by assuming birthdays occur on the same day of the week with equal frequency. So you're just as likely to be born on a Sunday as a Tuesday or any other day of the week. Now, here's going to be 2 different probabilities that we're going to calculate. 2 different probabilities. We're going to calculate the probability that 2 people are born on the same day of the week, and probability that 2 people are both born on a Monday. Now, they might sound like the same events that we're calculating the probability of, but they're actually different. Now, if we want to calculate the probability that 2 people are born on the same day of the week, there is no particular day that's specified, so the probability that the first person is born on the same day as the second individual, well, for any given day of the week, there's a 1/7 chance that the first person is born on that day, and there's a 1/7 chance that that second person is born on that same day. So the probability that 2 people are born on the same day is actually going to be 1/7. Why? Well, just ask that first person what day he or she was born. Suppose it's a Monday. There's a 1/7 chance that the second person will have the same birthday day of the week as the first person. So that's why that probability that 2 people were born on the same day of the week is 1/7. But calculate... Excuse me. Sorry about that. A technical glitch, just bear with me. Sorry about that. Here we go. Sorry about that. Don't know what happened there. But the second event was the probability that both people are born on a Monday. This is a different proposition compared to the first one. Second one here you're going to randomly select two individuals and calculate the probability that they were both born on a Monday. Well, there's a 1/7 chance that the first person was born on a Monday, and there's a 1/7 chance that the second person was born on a Monday. So 1/7 times 1/7 is 1/49. Notice we have the word "and" to mean that first person was born on a Monday and the second person was also born on a Monday. When you hear the word "and," that means multiply in the world of probability. So you multiply those individual probabilities, you get 1/49. Again, this is kind of a subtle idea here. These two events are separate from each other. So I'm going to just repeat what we said about part A here. The probability that two people were born on the same day of the week is going to be 1/7. If you ask the first person what day of the week that he or she was born on, suppose it's a Tuesday, then there's a 1/7 chance that the second person was born on that same day of the week. That's different than ask what's the probability that any two individuals that you select randomly, the probability that they were born on a particular day of the week. There's a 1/7 chance that the first person was born on that day of the week, and there's a 1/7 chance for that second person. So you multiply those individual probabilities, you get 1/49. Two different probabilities. Moving along here. Now, tree diagrams are useful in sorting out the number of ways that an event could happen. It also helps you calculate probabilities when there are two or more experiments or trials happening. Okay? Here's an example of a tree diagram. Suppose that we want to figure out how many ways could you get responses from two questions on a test. So suppose there are two questions on the test. The first question is true, false, and the second question is multiple choice with 5 choices. So take a look at this tree diagram that we've got here. This first question, there's two possible ways, true and false, of answering that question. And for each response for the first question, true or false, there are 5 possible choices for the second answer's response. You could have responses total for the exam or quiz of true followed by A, or true followed by B, true C, true D, true E, or false A, false B, false C, false D, false E. There, we've enumerated them, we've listed them completely. And there's a total of 10. 2 times 5 is 10, right? There's 2 choices for the first answer and 5 choices for the second one, for a total of 10. So you should be able to see all 10 outcomes. 10 possible combinations of answers. So the tree diagram is going to be very useful. We could extend this even further. If you had a third question, could be true, false, could be multiple choice, whatever. And for each branch, maybe this branch followed by this branch, you could have, so many choices for that third question. Our tree would grow to be terribly large, but you get the idea. Then you could count the total combinations of answers across all 3 questions by following the same sort of logic that you see here. So let's just kind of sum up what we've talked about in this lecture. We talked about calculating the probability when you have 2 or more events. Now, when you have an or separated those events, probability of A or B happening, that means adding. You're adding the individual probabilities, making sure that you adjust, when the events are overlapping. as you saw in the last section. But if you want to calculate the probability that the two events happen simultaneously or subsequently, you want to calculate the probability of event A and event B happens, the word and suggests multiplication. Taken into account, though, in adjusting as necessary, whether event B, the probability of it, depends on knowing what has happened with the first event A. If event B somehow depends on event A, then you will have to make that probability for B conditional on event A. But if event A and B are independent of each other, then you'll just simply multiply their individual probabilities. All right, so this summarizes everything that we've talked about in this section and the previous section. So you want to calculate probability of A and B happening. Well, are A and B independent? If they are, just simply calculate the product of their individual probabilities. If A and B are not independent, then condition B on A and calculate the probability of A times the probability of B conditioned on A. Okay? So with that, we are done for today. If this were a probability of A or B, remember that you are adding. But P and A, probability of A and B, probability of A and B, you multiply their individual probabilities. Okay, so that's it for today. Tomorrow we will take a look at multiplication rule involving complements and so forth. All right, we'll see you next time.